Good day. In this discussion video, we will be solving some examples of surface integrals of vector fields. We will be doing these items in the context of flux. Let's recall some formulas that we will be needing for today. Given a vector field f of xyz acting across a surface S, let D be the projection of S onto an appropriate plane of integration. It could be the xy plane, or the xz plane, or the yz plane. Suppose here that S is positively oriented. We have the following cases for S. If the surface has Cartesian equations, say z equal to g of x and y, then the flux of f across S can be computed as follows. It's the surface integral of f dot n d sigma, which is equivalent to the double integral over the region D of f of x, y, and g of xy standing for z, dot this vector, negative g sub x, negative g sub y, and 1. Okay? So that's the first equation. On the other hand, if S is parametrized by a vector-valued function, r of u and v, then the flux can be computed as follows. We have the double integral over d of f of r dot ru cross rv. Okay? So those are the two forms of the surface integral of a vector field, which we will be using to solve these 7 examples. Feel free to pause the video at any moment if you want to solve these items first. I will also pause for a moment. All right, so that's it. Let's try these items together. In each of these items, our task is to find the flux of the given vector field across the corresponding surface. And unless the surface is given a different orientation, we will assume that the surface is positively oriented. All right, let's start. With this first vector field, negative x plus 2y, x plus 2z, and 2y plus z, acting on the surface parameterized as follows: 2u, u plus v, and 2v, where u is between 0 and 3, v is between 0 and 1. All right, first let's look for a normal vector to the surface S. This normal vector need not be of length 1, no? Unlike in the formulation for your surface integral. So here, it will suffice if we just take a normal vector of this form, r sub u cross r sub v. And from the equation for r here, we have r sub u equal to 2, 1, 0. And for r sub v, it's going to be 0, 1, and 2. Okay? And from there, we can compute this cross product. First component 2, second component minus 4, third component 2. Okay? And from there, we can now compute your flux, which again is the surface integral of f dot n. And equivalently, it is going to be the double integral over the region D in the UV plane of f of r, with these components, dot ru cross rv dA. Solving for f of r, we get these components: 2v, 2u plus 2v, and 2u plus 4v. And then dot that vector, which we integrate over the region in the UV plane, v from 0 to 1, u from 0 to 3. Okay? And once we get this dot product here, we can do the double integration. So we get 4v minus 4u for the dot product. Integrating this with respect to u, or to v rather, gives us 2v squared minus 4uv, which we evaluate from v equals 1 to v equals 0, giving us this, 2 minus 4u. And we integrate that with respect to u, so that we get 2u minus 2u squared. evaluating it at u equals 3 and at u equals 0, gives us the flux of this vector field across the given surface. Answer, negative 12 units. Okay, so that's item number 1. Okay, let's do another example here. Different vector field, it's x, y, and 1, acting across the surface r of uv equal to u cos v, u sin v, and 1 minus u squared, where u is between 1 and 2, and v is between 0 and 2 pi. All right, like what we did in the previous exercise, we will get a normal vector for your surface, which is that r sub u cross r sub v. Now, r sub u is going to be cos v, sin v, and negative 2u. And r sub v is going to be negative u sin v, u cos v, and negative 2u. It's supposed to be for r sub u. R sub v has third component 0, sorry. All right. And when we get the cross product here, we should get this one. 2u squared cos v, 2u squared sin v, and u. Okay. So now we can compute your flux like this as the double integral over d of f of r dot ru cross rv. Now f of r, it's going to be just u cos v, u sin v, and 1 dot this vector, which we integrate over the region u from 1 to 2, v from 0 to 2 pi. Okay, and now we get that dot product. It's going to be 2u cubed plus u na lang. No? And note here that this integrand is independent of v. So we can do the trick of splitting this integral into 2 integrals, one involving just v and the other involving just u. Take note, it can only be done if all the bounds are constant, like this, and if the integrand can be separated into a product of a function of u and a function of v. Okay? So in this case, the function for v is going to be just 1, integrated from 0 to 2 pi. And the second function is going to be 2u cubed plus u, integrated from 1 to 2. Okay, so let's take the integrals there. First integral is going to be 2 pi. The second is going to be u to the 4 over 2 plus u squared over 2, evaluated from u equals 2 to u equals 1. And that's going to be at u equals 2, that's 10. Minus at u equals 1, it's going to be 1. So that gives us our final value for the flux of F across S, 18 pi. Okay, so that's item number 2. All right. Now we've dealt with 2 exercises involving parametric surfaces. Let's check out if your surface is Cartesian. Okay, so the next 5 items will be on Cartesian surfaces. For exercise 3, we will find the flux of the vector field 2yj hat plus 3zk hat across the portion of the plane z equals 3x plus 2 inside the cylinder x squared plus y squared equals 4. Okay. So here, since the vector field is acting across the plane, then it will make sense if we take this as your surface z equals g of xy. That's 3x plus 2. So that gives us the following computation for your normal vector. Yung template kanina, negative g sub x, negative g sub y, and 1. And noting here, we have g sub x equal to 3 and g sub y equal to 0. So we have that. Normal vector negative 3, 0, 1. Okay? So that will now allow us to compute your flux as follows. F of x, y, and z, which is 3x plus 2, dot negative 3, 0, 1. Now, f here can be simplified into the following vector, 0, 2y, and 3z. That's 9x plus 6 dot this vector, which is equal to, yung dot product will be equal to 9x plus 6 integral over the region D. Okay, region D, ano kaya yun? No? Note here that the description of the surface involves the cylinder x squared plus y squared equals 4. No? It contains your surface. So maybe we could take that as your region D, or rather yung version niya sa 2D. In this case, the xy plane with equation x squared plus y squared equals 4, which is a circle of radius 2. Okay? So now we use that fact to evaluate the following expression for the flux from the previous slide. It's going to be, well, circle yan, ano? So maybe it would be better if we switch to polar coordinates, wherein we can express this double integral first before switching to polar. We can use linearity muna. By linearity, we mean we could split the double integral into 2. First, 9x muna, tapos 6 dun sa kabila. Okay? So, double integral of 9x plus double integral of 6. Okay? And now we invoke the switch to polar. For the first one, we have bounds for theta, 0 to 2 pi, and bounds for r, 0 to 2. Because this circle has equation r equals 2 in the polar plane. Okay. And then we have 9x, which in polar is 9r cos theta. And then dA in polar is r d theta. Okay. So that's the first double integral. Now what about the second one? Well, we have double integral of dA. I hope this is familiar. No? This gives precisely the area of your region D, which is a circle of radius 2. Ito. So hopefully, maalala pa natin ang area ng circle. Okay? All right. So we will do that for the second term. And for the first term, we will do yung kaninang ginawa natin, splitting your integral into 2. Kasi the bounds are constant and the integrand is a product of cos theta, giving rise to its own integral, and 9r squared. So may sarili siyang integrand. No? So that's the first term. For the second term, ito na, area of the region, that's going to be 6 times pi r squared. So that's pi, radius squared, 2 squared. Okay? And from there, we can get your integrals for the first part. That's going to be sine theta from 2 pi to 0, which is going to be 0 eventually, plus or times 3r cubed from 2 to 0, plus 24 pi for the second term. And then finally, we will have the first term is 0 times something actually. Let's just put it there. It's 24. So that's 0 plus 24 pi, giving you the flux of F across the surface S. So that's item number 3. Okay. Okay, now let's do item 4. Here, ang vector field ay xk hat lang. As for the surface, it will be the portion of the paraboloid z equals x squared plus y squared below the plane z equals y. But this time, take note, my orientation na yung surface. Downward unit normal. Downward. Usually, we associate it with a negative. No? So let's see how that will affect our solution. It will affect our solution by setting first yung surface natin as the g of xy. Z equals x squared plus y squared. Now, since we have a downward unit normal na kailangan, we will alter your normal vector a bit by considering a negated version. Kanina negative g sub x yun, comma negative gy, comma 1. But this time, the normal vector will be the negative version. G sub x, G sub y, -1. Okay? Actually, ang trick dito, you can focus on the 1 or -1 na term. Kapag negative yung term, ibig sabihin, yun yung magre-reflect nung negative orientation. Downward, or minsan inward, those terms, no? Or in the negative something direction, okay? So that gives us your normal vector here in this example, which upon solving for the components here, the G sub x and the G sub y, give us that vector. Okay, so from there, let's get your flux. Idiretso na natin dun sa double integral. Ayan. So we have f of x, y, z. Z is x squared plus y squared. Dot that. However, f here only has a k component na non-zero. So, siya lang yung matitira dyan. Okay? And when we take its dot product with the vector here, we'll just get negative x dA over the region D. Okay, o ito ang tanong. Nasaan yung region? Well, we will need a projection from the formulation kanina, no? We will need a projection of the surface onto an appropriate plane. Maybe let's try the xy plane for this one, no? Kasi pwedeng i-equate itong dalawang z na ito to get a curve of intersection. Okay, so let's do that. So for the region D, we project the surface S onto the xy plane, which in terms of equations, as we noted, is equivalent to equating the two z's. And since one of the parts here involves x squared plus y squared, baka makatulong na mag-polar ulit tayo, no? So in particular, this left part is r squared, and this right part is going to be r sine theta. And since we want r to be non-zero, we have that. R equals sine theta. Okay? So that curve, let's just graph it a bit here. That's your region R, or D rather, which is traced once from 0 to pi for theta. 0 to pi ang theta nito, no? So now, we are ready to evaluate your flux like this. So we switch to polar with theta from 0 to pi, R from 0 to sine theta. Okay? And then x here is r cos theta, and dA is r d theta. Okay? Now note here that one of the bounds in the innermost integral has a theta, so hindi tayo pwede mag-split. No choice tayo, we will iterate the integral. Yeah, we can throw the negative outside, and then we have integral of r squared, which is r cubed over 3 from 0 to sine theta. Tapos may cos theta d theta pa dyan. So we have negative of 1/3 sine cubed theta minus 0 times cos theta. Okay? And then at this point, maybe a little u sub will help. Let u be sine theta, du over here, cos theta, d theta. So meron tayong u cubed, bale, integral u to the 4 over 4. So sine to the 4 over 4 yan. Evaluated from pi to 0, but those values give sine theta equals 0. So all in all, this flux is just 0. Okay? So the entire flux is just 0. Okay? So that is item number 4. We will pause here for the first part of our video. In the second part, we will do exercises 5 through 7. Here, preview lang, iba na yung direction, no? Iba na yung orientation ng 5 and 6. Yung 5 sa positive y direction, yung 6 sa negative x direction. So let's pause here for a while. We will return with 5, 6, and 7.